So the last thing I'd like to cover today are some usage considerations to keep in mind when you apply Java condition objects in practice. Condition object is a highly flexible synchronization mechanism. You can do lots of interesting things with it. It's very powerful. In particular, it allows threads to cooperatively suspend or resume their execution based on shared state, shared mutable state, of course. And so as we saw with the array blocking queue, the different threads, T1 and T2 and so on, could take turns sharing a critical section, making progress when they can and blocking when they can't make progress. So as you can see here, you can see that thread T2 is blocked on a condition object, thread T1 is running, and then thread T1 can go ahead and park itself and wait, and then thread T2 can come back in, and so on and so forth. And even more, as we see here, you can also keep other threads at bay out of the critical section altogether, while the other threads take turns coordinating their actions. Another really nice feature of condition object is it can be used to define multiple condition objects within a user-defined Java object. And that, of course, is the benefit relative to the earlier Java built-in monitor object. Technically speaking, under the hood, each condition object contains its own separate wait set, which is implemented by a queue of waiting threads. So those threads and those queues don't compete with each other. They are separate. Of course, as is always the case, not everything is unicorns and rainbows. So you have to use condition objects very carefully to avoid various hazards and concurrency problems. So here's one thing that you almost always want to follow. There's rare occasions where this doesn't apply, but it's almost always the case that you want to wait on a condition object in a loop, just like we saw when we were implementing our array blocking queue. So for both take and put, they're going to be loops, and they're going to make sure that the conditions are satisfied before you can proceed, right? That's the guarded suspension pattern, as we talked about before. And the reason for doing this is you need to be able to test and or retest the state, the shared mutable state that's being waited upon, since it may change in a somewhat unexpected way due to the inherent non-determinism of concurrency. So concurrency is inherently non-deterministic, and this particular pattern or idiom is just par for the course when you deal with that particular fact. Another reason that you need to use the condition objects in a loop is to guard against something called spurious wake-ups. And this is a very, very esoteric problem. You should read the link at the bottom of the page for more details about what a spurious wake-up is. But apparently in some multiprocessor systems, or perhaps even today's multi-core systems, sometimes a condition variable will be signaled even when nobody called signal. Now, I honestly have never seen that happen in practice, but you just need to be prepared for it. And so that's yet another reason why you wait in a loop, because you may not have actually been signaled at all, and the state may not have changed, and yet you'll wake up anyway. So that's kind of weird, but you can read more about that at the link below. It's one of those sort of phantom problems. I'm not entirely sure if it's ever happens these days, but you need to be prepared for it and guard against it. So the bottom line is spurious wake-ups can occur if the thread is awoken from its waiting state, even though no user-level thread signaled the condition object. Condition objects are always used with locks or with a lock. Condition objects can share a single lock. You can have multiple condition objects sharing the same lock, as we did with array blocking queue. And we need to do this in order to avoid something called the lost wake-up problem. And you can read more about the lost wake-up problem at the link below. But basically what that would entail would be that a thread calls signal or signalAll. Another thread occurs between the test of the condition and the call to await and steals the wake-up, and therefore no threads are waiting. And so as a result, the wake-up is lost. And so the way to avoid this is actually quite simple with Java condition objects. Always make sure you call signal or signalAll with the lock held. And if you do that, you should never have a problem with lost wake-up. If you don't do that, if you try to get too clever, then you can end up with lost wake-up bugs. Await internally releases and reacquires its associated lock. And that's not something you have to do explicitly. That's done by the implementation of the await method deep inside the bowels of the abstract queued synchronizer framework and its condition object implementations. Another thing to be aware of, and this is really subtle, but at least it's tractable with with Java condition objects, unlike being less tractable or more expensive and more convoluted with Java built-in monitor objects. And that's, how do you choose between signal and signalAll? So as a general rule of thumb, you should try to stick with signal because it's more efficient. It just wakes up one thread and thereby avoids this so-called thundering herd problem. So make sure you read about the thundering herd problem. It's a problem that will undoubtedly show up on a quiz. So it's good to be aware of what it is and why you shouldn't do it, and also how to avoid it. There's a description of how to avoid this here when we think about the array blocking queue. So we're going to use the implementation of the array blocking queue to demonstrate the issue of choosing between signal and signalAll. So you should use signal instead of signalAll if there are two conditions. One is uniform waiters, and the other is one in and one out. So uniform waiters means that there's only one condition expression that a given call to await is waiting for, and that is essentially the same condition. And all the threads that are part of that wait set are all waiting on exactly the same condition. So you can see here, if you're a consumer thread and you want to take something out of the array blocking queue, all consumer threads are all waiting on exactly the same condition, which is while count equals 0, await. And so there's not a different condition that they're waiting on. They're all waiting on the same condition with the same shared mutable state. And then the second property that needs to apply in order to use signal rather than signalAll is one in and one out. And what that means is that a signal on condition object will enable at most one thread to proceed at a time, which is exactly what we want with our array blocking queue. When you call signal, you're waking up the next waiting thread, if there is one, in order to be able to do its thing. If you don't have these properties, then you probably need to use signalAll. The Java array blocking queue satisfies both of these conditions, which is why we're able to get away with using signals. Another thing to keep in mind, and I've run into this almost every year with some of the later programming assignments we're going to do, condition object inherits the wait, notify, and notify all methods from Java object, just like every other Java reference type. However, do not mix and match these methods. Do not call wait on a condition object and then call signal on the same condition object, because nothing good will happen. Nothing good will come from that. So once you start using condition objects, you should pretend as if wait, notify, and notify all do not exist. Even though it's perfectly valid to call them, they don't have the right behaviors or semantics when used in conjunction with await, signal, and signalAll. This is a very, very simple bug to make, and your compiler will not save you from doing this. Another thing to remember is you should strive to name the condition object fields to reflect their usage. So as you see, we had a not empty condition and a not full condition. And the not empty condition was used to wait until the condition is not empty, and not full is used to wait until the condition is not full. So I think that's pretty intuitive, but just a good thing to get in the habit of remembering that you're waiting for the condition to not be something. Condition object is used quite extensively within Java util concurrent, and it's implemented in Java util concurrent locks, and there's some uses of that in some of the various classes defined there. However, in practice, you almost never access condition objects directly in your code. You almost always hide them behind some higher level abstractions. And of course, the classic example of this, and almost in some ways the defining example, is using condition objects to implement array blocking queue and linked blocking queue. So those in my mind are kind of the canonical uses of condition objects. There are other uses of condition object in other Java synchronizers, but by and large, the primary way in which they're used is for these thread-safe queues, the producer-consumer queues that block when the queue is empty or block when the queue is full. So that's the end of the overview of the Java condition object usage considerations. Now you should be quite well prepared to implement the simple semaphore, which is part of your assignment 2B.